There is a moment in the life of every civilization when it looks up, not just to wonder, not just to dream, but to reach. For most of human history, that reach stopped at the horizon, then it stopped at the clouds, then at the edge of the atmosphere. And for a brief, extraordinary window of time, a window we are still living through, it reached past planets, past the edges of everything we had ever called our solar system. This is the story of two machines that were never meant to last this long, machines that were built with 1970s technology, computers with less processing power than the phone sitting in your pocket right now. And yet, against all reasonable expectation, they are still out there, still moving, still, for now, whispering back to us across a distance, so vast it nearly defies human comprehension. This is the story of Voyager. September 5th, 1977. Cape Canaveral, Florida. The air smells of salt and rocket fuel. A Titan Centaur rocket stands on the launch pad, carrying aboard a spacecraft the size of a small car, roughly 815 kilograms at launch, with a large dish antenna stretching nearly 4 meters across, and a collection of scientific instruments mounted on long booms, extended outward like the arms of a curious child reaching to touch something for the first time. Its name is Voyager 1. 2 weeks earlier, on August 20th, its twin, Voyager 2, had already left Earth. Despite the names, Voyager 2 actually launched first. The numbering was based not on launch order, but on which probe would reach the outer planets sooner. Voyager 1 was on a faster, more direct trajectory, so it was given the number 1. The mission, as officially stated, was planetary. Both spacecraft were designed to conduct close flyby studies of Jupiter and Saturn. Voyager 2 would go further. It was placed on a trajectory that would allow it to visit Uranus and Neptune as well. This was only possible because of a rare alignment of the outer planets, an alignment that happens once every 176 years. That allowed a spacecraft to use each planet's gravity as a slingshot to the next. NASA called the Grand Tour. They would not get another opportunity like it until the 24th century. But there were people at NASA, scientists, engineers, dreamers, who understood something else about these missions from the very beginning. They understood that a spacecraft given enough velocity to escape the gravitational pull of the sun would not stop. There was nothing to stop it beyond the planets, beyond the edge of the heliosphere, the vast bubble of solar wind that surrounds our solar system. There was open interstellar space, and a spacecraft moving at roughly 17 kilometers per second would simply keep going for thousands of years, for millions of years, perhaps forever. And so, almost as an afterthought, though it was anything but, someone asked, what if something finds it? That question led to the creation of what is now one of the most poetic objects ever made by human hands, the Voyager Golden Record. But we will come to that later. For now, September 5th, 1977. The countdown reaches 0. The engines ignite. The ground shakes. And Voyager 1 rises into Florida sky, accelerating through the atmosphere, punching through the thin blue line that separates the world we know from everything else. Within minutes, it is in orbit. Within hours, it is on its way to Jupiter. The people watching from the ground, the engineers, the scientists, the families who had come to watch, they cheered. They took photographs. They celebrated. None of them would live to see where it was going. There is something worth pausing on here before we follow Voyager into the dark. When you send something into space, truly into space, beyond the reach of gravity, beyond the influence of the sun, you are making a statement that transcends science. You are saying, we were here. You are creating an artifact that will, in all likelihood, outlast your civilization, outlast your species, outlast the sun itself, which will expand and swallow the Earth in roughly 5 billion years, long after Voyager has drifted far beyond its reach. Voyager 1 and Voyager 2 are the farthest objects ever launched by human beings. They are the only human-made objects that have left the solar system, and they're still going. Jupiter comes first. Voyager 1 reaches Jupiter in March of 1979, about 18 months after launch, and what it finds there shatters expectations. We knew Jupiter was large. We knew it had moons. But what Voyager showed us was something nobody had fully anticipated. Jupiter was not just a large, passive gas giant sitting in the dark. It was a world of violent, extraordinary complexity. The Great Red Spot, a storm that had been observed from Earth for centuries, was revealed in stunning detail. A hurricane larger than the entire Earth, with winds screaming at hundreds of kilometers per hour, rotating counterclockwise with a kind of terrible, ancient patience. Voyager's cameras showed cloud bands of orange and white and brown, swirling and folding into each other in patterns that looked almost alive. But the moons were perhaps the greatest revelation. Io, the innermost of Jupiter's large moons, was found to be the most volcanically active body in the entire solar system. Voyager 1's cameras caught an eruption in progress, a plume of volcanic material rising 300 kilometers above the surface. No one had expected this. Not one geological model had predicted it. The discovery was made almost accidentally by a navigation engineer named Linda Morabito, who spotted the plume while reviewing an image taken for a completely different purpose. Europa, another of Jupiter's moons, showed a surface covered in a network of cracks and lines, like the shell of a broken egg. Beneath that icy surface, scientists suspected there might be a liquid ocean. That hypothesis has since grown into one of the most significant questions in the search for life beyond Earth, and remains so today. Voyager 2 followed Voyager 1 to Jupiter in July of the same year, confirming and expanding on these discoveries. Then they both continued onward to Saturn with its rings. There's perhaps no object in the solar system more immediately breathtaking than Saturn seen up close. From Earth, even through a telescope, the rings are beautiful, a flat, perfect disk of light circling a pale gold planet. But Voyager revealed that those rings are not a simple disk at all. They are made of thousands of individual ringlets, billions of pieces of ice and rock, each one in its own orbit, the whole system governed by gravitational interactions so intricate that scientists are still working to fully understand them. Voyager 1 reached Saturn in November 1980. Voyager 2 arrived in August 1981. Among Saturn's moons, one stood out above all others: Titan. Titan is Saturn's largest moon, and it is unique in the solar system. It has a dense atmosphere, thicker than Earth's, made primarily of nitrogen. Voyager 1 was directed toward Titan for a close flyby, specifically because scientists wanted to study that atmosphere in detail. They knew this would alter Voyager 1's trajectory permanently, pulling it up and out of the plane of the solar system, away from Uranus and Neptune. It was a deliberate choice. Science required it. But Titan's thick orange haze blocked Voyager 1's cameras entirely. The atmosphere was there, yes, but the surface was hidden. We would have to wait decades more for that secret. The Cassini-Huygens mission, which arrived at Saturn in 2004, finally landed a probe on Titan's surface and found lakes of liquid methane. Voyager 1's grand planetary tour was over after Saturn. It was now on its unique trajectory, heading upward and outward, away from the solar system's plane, on a path that no deliberate steering could ever have corrected. It was headed for interstellar space. Voyager 2, however, still had work to do. Using Saturn's gravity as one final slingshot, it continued toward Uranus, which it reached in January 1986, and then Neptune in August 1989. These were the first, and to this day, the only close-up observations ever made of these two planets by a spacecraft. Uranus turned out to be a world tilted almost completely on its side, rotating at nearly a 98-degree axial tilt, essentially rolling along its orbit rather than spinning upright. Its rings were narrow and dark. Its moon showed evidence of dramatic geological activity. Neptune, perhaps the most unexpectedly beautiful destination of all, showed a deep, vivid blue, the result of methane absorbing red light in its atmosphere. Voyager 2 discovered a massive storm system there, the Great Dark Spot, comparable in scale to Jupiter's Great Red Spot. It also discovered that Neptune's largest moon, Triton, orbits in the opposite direction of Neptune's rotation, suggesting it was captured by the planet's gravity rather than formed alongside it. Triton also showed active geysers, erupting nitrogen gas from its surface. A frozen, distant world, breathing. After Neptune, Voyager 2 joined its twin, heading for the edges of the solar system and beyond. But before we follow them there, we must speak of photograph. February 14, 1990. Voyager 1 is now approximately 6 billion kilometers from the Sun, with Earth appearing as little more than a point of scattered light in the distance. At the request of the astronomer Carl Sagan, NASA turns Voyager 1's camera, for the last time, back toward the inner solar system. What it captures is an image that has never left the human consciousness since. In a wide-angle photograph of the solar system, taken from a distance no human instrument had ever looked back on before, Earth appears as a tiny point of light, less than a pixel across, barely visible against the vastness of space. A pale blue suspended in a sunbeam. Carl Sagan described it this way, and these are not my words, but is because no paraphrase could do them justice. He wrote that this distant image of our tiny world was, in his view, a powerful statement about human pretension. That on that, everyone you ever heard of, every human being who ever lived, every king, every peasant, every young couple in love, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust, suspended in a sunbeam. After this photograph, the cameras were turned off. There was no scientific reason to keep them on. The mission of planetary exploration was complete. The instruments that remained were different, designed not to photograph, but to listen, to measure, to sense the invisible magnetic fields, charged particles, plasma waves, cosmic rays, the things you cannot see, but that fill the space between the stars. Voyager's new mission had begun, not a tour of planets, something older, quieter, more profound, a crossing into the unknown. Let's talk about where space actually begins. This sounds like a simple question. It is not. Most people, when they think about the edge of the solar system, think of the last planet, Neptune, the outermost giant, nearly 4.5 billion kilometers from the Sun. Beyond Neptune, in the popular imagination, there is simply nothing, empty space. But that is not quite right. The Sun does not end at Neptune. Its influence extends far, far beyond. In fact, the Sun is constantly exhaling, a continuous stream of charged particles, mostly protons and electrons, flowing outward in all directions at speeds of hundreds of kilometers per second. This stream is called the solar wind, and it does not stop at Neptune. It keeps going, expanding outward in a vast bubble that surrounds the entire solar system. That bubble has a name, the heliosphere. The heliosphere is the true domain of our Sun. Everything inside it, every planet, every moon, every asteroid, every comet, exists within this invisible shield, bathed in the Sun's constant outward breath. The solar wind deflects much of the radiation and charged particles that come from interstellar space, from dying stars and cosmic events in the galaxy beyond. Without the heliosphere, life on Earth would face a very different radiation environment. But the heliosphere has an edge. At some point, the solar wind slows down. It has been expanding and cooling for billions of kilometers, and eventually it runs into material of interstellar space, the thin, cold plasma that fills the galaxy between the stars. Where these two meet, the solar wind decelerates rapidly. Scientists call this boundary region the termination shock. Beyond it, the solar wind still flows, but it is turbulent now, compressed, mixed with interstellar material. This chaotic region is called the heliosheath, and at the very outer boundary, where the solar wind finally stops entirely, where our Sun's breath can go no further, is a boundary called a heliopause. The heliopause is, in the most meaningful physical sense, the edge of the solar system. Beyond it, interstellar space, the space between the stars, a region that had never, in all of human history, been directly sampled by any instrument we had ever built until Voyager. For decades, scientists have been watching Voyager's instruments, waiting. Theoretical models predicted roughly where the heliopause would be, but models are models. Nobody knew for certain what the crossing would look like. Nobody knew exactly how thick the heliosheath would be, how turbulent, what the plasma conditions would be on the other side. Voyager 1 began giving hints as early as 2004, when its instruments detected the termination shock, the first acceleration of the solar wind. It crossed fully to the heliosheath over the following years, its instruments registering changes in particle density, magnetic field orientation, and the balance between solar and interstellar particles. And then, in August 2012, something changed. The data coming back from Voyager 1 showed a sudden, dramatic drop in the density of particles from the Sun, and a simultaneous, equally dramatic rise in cosmic rays from outside the solar system. The magnetic field direction shifted. The plasma around the spacecraft was no longer solar wind. Voyager 1 had crossed the heliopause. It had entered interstellar space. The announcement came on September 12, 2013, after months of careful analysis to make sure the data was being interpreted correctly. And when it was confirmed, it was understood for what it was, one of the genuine milestones in the history of exploration. For the first time, a human-made object was in the space between the stars, not in orbit around a planet, not in the outer reaches of the solar system, truly, physically, in the interstellar medium. The distance at that moment, approximately 18.8 billion kilometers from Earth, about 122 times the distance from the Earth to the Sun. A signal from Voyager 1, traveling at the speed of light, took about 17 hours to reach us. Voyager 2 followed a different path, heading south, below the plane of the solar system, toward the constellation Sagittarius, and crossed the heliopause later on November 5th, 2018, 6 years after its twin. What made Voyager 2's crossing particularly valuable was that its plasma science instrument, an instrument that had failed on Voyager 1 years earlier, was still functioning. This meant that for the first time, scientists could directly measure the plasma conditions on both sides of the heliopause simultaneously. What they found was surprising in its detail. The heliopause, it turned out, was sharper than many models had predicted, almost like a wall, rather than a gradual transition. The temperature on the interstellar side was higher than expected. The magnetic field at the boundary was more complex, and the density of interstellar plasma was different at the two crossing points, north and south, suggesting that the heliosphere is not a perfect sphere, but an asymmetric shape, pushed and pulled by the uneven pressure of the interstellar medium around it. These were not abstract findings. They were direct measurements from the only instruments ever to exist beyond our solar bubble. No telescope can observe the heliopause from the inside. The very solar wind that fills the heliosphere scatters the wavelengths needed to image it. Voyager's in situ data remains, to this day, irreplaceable and unique. Both spacecraft are now beyond the heliopause. Both are, by any meaningful definition, in interstellar space, and both are still sending data back. There's something quietly staggering about this. The Voyager spacecraft were designed and built in the early 1970s. Their computers operate on 69.63 kilobytes of memory. A modern USB drive you could lose in the bottom of a bag contains more computational power than both Voyager spacecraft combined by a factor of millions. And yet here they are, still functioning, still measuring, still transmitting. The signal they send back to Earth is extraordinarily faint. By the time it arrives, after traveling billions of kilometers, it has weakened to about 20 billion times below what it takes to power a single LED light bulb. NASA's Deep Space Network, a system of enormous dish antennas in California, Spain, and Australia, strains to hear it, filtering the signal from the background noise of the universe. Every piece of data that comes back is a small miracle of engineering, patience, and human ingenuity. But it will not last forever. This is a part of the story that requires us to sit with something uncomfortable. Voyager 1 and Voyager 2 are dying. Not dramatically, not in an explosion, not in a collision, not in some sudden catastrophic failure. They are dying the way all things powered by finite energy die. Slowly, quietly, instrument by instrument, as the power runs out. Both spacecraft are powered by radioisotope thermoelectric generators, RDGs. These are devices that convert the heat produced by the radioactive decay of plutonium-238 into electricity. They require no sunlight. They require no fuel in the conventional sense. They simply use a natural, unstoppable process of radioactive decay to produce a steady, reliable stream of power. When Voyager launched in 1977, each RTG was producing roughly 470 watts of electrical power. That is less than 5 standard light bulbs. But plutonium-238 decays, slowly, predictably, with a half-life of about 87.7 years, but relentlessly. Each year, the power output drops by roughly 4 watts. By the mid-2020s, each spacecraft operates on roughly 2/3 of its original power, and that fraction continues to shrink. And that power must be shared between keeping the spacecraft warm enough to function, maintaining communication systems, and running whatever science instruments remain active. The math is unforgiving. And so, over the years, instruments have been turned off, one by one. Each shutdown is a small loss, a sensor that will never again send data, a measurement that will never be taken. As of 2026, Voyager 1 is carrying 2 functioning science instruments, a magnetometer, which measures magnetic fields, and a plasma wave subsystem, which listens to the electromagnetic waves in the interstellar medium. Earlier in 2025, its cosmic ray subsystem was powered down to conserve energy, and in April 2026, the low-energy charged particles experiment, an instrument that had been measuring the density and composition of charged particles in interstellar space since 1977, was shut off as well. Voyager 2 still carries 3 functioning science instruments as of the same period, including its own cosmic ray subsystem, which scientists are particularly eager to keep running, as well as a magnetometer and plasma wave subsystem. Each instrument that goes dark takes with it a piece of our ability to understand interstellar space directly. There is nothing else out there to replace these measurements. No other spacecraft has reached this distance. No other mission is currently on its way. But the engineers at NASA's Jet Propulsion Laboratory are not giving up without a fight. In early 2026, they announced an ambitious plan, one that the team has informally called the Big Bang. The idea is to attempt a software and power management upgrade to Voyager 1, similar in spirit to complex remote computer repairs that the team has successfully performed before. In 2023 and 2024, Voyager 1 experienced a serious communications crisis. A corrupted chip caused the spacecraft to begin transmitting garbled, unintelligible data for months. Engineers, working across a signal delay of nearly 23 hours each way, managed to diagnose the problem, identify a workaround, and restore full science communications. It was by any measure an extraordinary feat of remote engineering. The Big Bang upgrade is intended to squeeze additional operational life from the spacecraft by reallocating power more efficiently. The plan as of mid-2026 is to test the procedure on Voyager 2 first, which has slightly more power margin and is closer to Earth, making it a somewhat safer test subject. Tests are planned for the middle of 2026. If they succeed, the team will attempt the same procedure on Voyager 1 no sooner than July 2026. If it works, there is even a possibility that some previously shut down instruments could be reactivated. Nobody is certain it will work, but the team is trying, because every additional month of data from interstellar space is data that cannot be obtained any other way. And meanwhile, Voyager 1 is approaching a milestone that no human-made object has ever reached before. In November 2026, on or around November 13th to 15th, According to current projections, Voyager 1 will be one full light day from Earth. One light day, the distance at light, traveling at approximately 300,000 kilometers per second, the fastest anything in the universe can move, covers in 24 hours. That is approximately 26 billion kilometers. When Voyager 1 reaches that point, a signal sent from Earth at the speed of light will take 24 hours to arrive. And Voyager's reply, also traveling at the speed of light, will take another 24 hours to return. A simple question, an answer will span 2 full days. There is no human analogy for this. No ocean crossing, no expedition to a distant continent. No journey to Moon or Mars comes close. The Moon is about 1.3 light seconds away. Mars, at its farthest, is about 22 light minutes away. One light day is a distance that makes even interplanetary travel seem like a walk to the next room. And Voyager 1 reached this distance moving at 17 kilometers per second for 49 years. Voyager 2, on its slightly slower and different trajectory, will not reach one light day from Earth until approximately 2035, somewhere in the mid-2030s. The exact timing depends on how successfully the power management strategies play out. Both Voyager spacecraft will fall below the minimum power threshold required to operate any science instrument at all. After that, they will still transmit engineering data for a little while longer. Heartbeat signals, essentially. Small packets of information about the spacecraft's own health, temperature, voltage, attitude. Enough to confirm that it is still there, still functioning at a basic level. And then, sometime in the late 2030s, or perhaps, if the team's best efforts succeed, into the early 2040s. Even that will stop. The signal will go silent. For the first time in more than 6 decades, there will be no data coming back from Voyager. No heartbeat. No whisper across the dark. Just silence. And in that silence, the spacecraft will continue what they have always done. They will keep going. There is a particular kind of loneliness that comes not from being abandoned, but from moving beyond reach. Think about what it means for a signal to go silent. For over 60 years, Voyager has been a conversation. A slow one, answers taking hours and most of the day, but a conversation nonetheless. Engineers send a command. Voyager receives it, executes it, reports back. Scientists look at the data, form new questions, send new instructions. There's a relationship there, a thread impossibly thin, stretched across billions of kilometers, but real. When the power finally drops below the minimum threshold, when the last instrument goes dark and the last heartbeat transmission fades into the background noise of the universe, that thread will be cut, not because Voyager stopped moving, not because it was destroyed, simply because there is no longer enough energy left, after nearly 70 years of radioactive decay, to power even the most basic transmitter. Voyager will still be there. It will still be moving, essentially unchanged in its trajectory, because in the near vacuum of interstellar space, there is almost nothing to slow it down. It will still be carrying everything it was built with. Its instruments silent. Its antenna, no longer held in place by the thrusters that have kept it pointed toward Earth all these decades, will slowly drift from its alignment, as there will be nothing left to correct it and the stars shift around it. Its golden record, intact, but we will not know where it is. Not precisely. Not anymore. We will be able to calculate its position. Physics is reliable, and we know its velocity and trajectory with great precision, but we will not be able to confirm. We will not be able to ask. We will be doing mathematics on a ghost. There's a word that scientists use for what Voyager will become after the signal stops. Derelict. It is a word borrowed from maritime law. A derelict vessel is one that has been abandoned at sea, drifting without crew, without control, without destination. The word carries within it both a sense of loss and a strange kind of freedom. A derelict vessel is not destroyed. It is simply no longer guided. Voyager will become the loneliest derelict in history. And yet, and this is the part that philosophy insists we sit with, it will not have failed. It will have done everything it was ever asked to do, and more. It will have traveled farther than any human-made object in history. It will have crossed the boundary of the solar system. It will have measured the interstellar medium directly with its own instruments and sent that data home. It will have carried on its body a record of everything we thought was worth saying about ourselves. The silence, when it comes, will not be a failure. It will be a graduation. But let us not move past this moment too quickly, because there is something deeply human about losing contact with something you have loved and tracked for decades. The engineers and scientists who have worked on the Voyager mission, some of them for their entire careers, will feel that silence differently than the rest of us. To them, Voyager is not an abstraction. It is a project they inherited, maintained, repaired, argued about, stayed up nights worrying over. The 2023 communications crisis, when Voyager 1 began transmitting garbled data due to a corrupted chip, was described by the team's deputy project scientist at Princeton University as, in her words, a nail-biter. Months of uncertainty, of trying to diagnose a problem on a computer 47 years old, across a signal delay of nearly a full day each way. They fixed it. That kind of dedication, that refusal to let go, is itself a statement about what this mission means to the people inside it. The Voyager program has now outlasted most of the careers of the people who built it. Its current team inherited it from people who are now retired or gone. And when the signal finally stops, it will be this generation or the next that hears the last transmission. Some of them will remember that moment for the rest of their lives. And after the silence, what? After the silence, Voyager enters a phase of its journey that no human instrument will ever observe directly. A phase that will last not for years, not for decades, but for thousands upon thousands of years. A phase we can only describe in a language of mathematics, of orbital mechanics, of stellar cartography. A phase that belongs not to science as we practice it day to day, but to something closer to deep time, the kind of time that geology speaks in, that evolution speaks in, the kind of time that makes all of recorded human history feel like a single breath. This is the phase we need to talk about now. Let us travel forward in time. Not years, not decades, thousands of years, tens of thousands, hundreds of thousands. This is not speculation for its own sake. The physics of Voyager's trajectory is well understood. Astronomers and researchers, using data from the European Space Agency's Gaia mission, which has mapped the positions and velocities of nearly 2 billion stars with extraordinary precision, have integrated the future paths of the Voyager spacecraft and compared them to the projected positions of stars in our galactic neighborhood. The results were published in peer-reviewed research. What follows is based on that work. But let us begin at the beginning of Voyager's long solo journey. Right now, in 2026, Voyager 1 is moving through what scientists call the local interstellar medium, the thin, cold soup of gas and plasma that fills the space between the stars and our corner of the Milky Way. It is traveling at roughly 17 kilometers per second relative to the Sun. That sounds fast, and in human terms, it is extraordinary. But against the scale of interstellar distances, it is almost heartbreakingly slow. The nearest star system to our own, the Alpha Centauri system, which includes Proxima Centauri, is approximately 4.24 light-years away. At Voyager 1's current speed, it would take roughly 73,000 years to cover that distance. And Voyager 1 is not even headed in that direction. Space is not empty in the way we sometimes imagine it. Between the stars, there is gas, there is dust, there are magnetic fields threading through the interstellar medium like invisible currents in a dark ocean. There are shock waves from ancient supernovae, still slowly expanding outward tens of thousands of years after the explosions that created them. There are clouds of dense material, regions where the gas between the stars thickens, where the dust is heavy enough to dim the light of background stars. Voyager will pass through all of this, silently, without instruments to record it, a bottle cast into a cosmic ocean, drifting on current it cannot feel. For approximately the first 20,000 years of its solo journey, Voyager 1 is still, technically, within the gravitational influence of the Sun. The Sun's gravity extends much farther than the heliosphere, much farther even than the planets. It extends outward into a vast, spherical shell of icy bodies and frozen comets, called the Oort cloud. The Oort cloud is one of the least observed structures in the solar system. We have never directly seen it, only inferred its existence from the long-period comets that occasionally fall inward toward the Sun, taking thousands of years to complete a single orbit. It is thought to extend from roughly 2,000 astronomical units from the Sun to perhaps 100,000 astronomical units, or about 1.6 light-years. At its outer edge, the Sun's gravity is so weak that passing stars can perturb the orbits of objects within it. It will take Voyager 1 approximately 20,000 years to enter the Oort cloud, and perhaps another 10,000 to 20,000 years to pass fully through it. Only after that, roughly 30,000 to 40,000 years from now, will Voyager 1 be, for the first time, truly free of the Sun's gravitational embrace. At that point, other stars will pull on it more strongly than the Sun does. The spacecraft will have changed hands, gravitationally speaking, from our star's domain to the open democracy of the galaxy. Now let us talk about what comes next. In approximately 40,000 years, Voyager 1 will make its closest approach to another star. That star, cataloged under two different designations, AC plus 793888 and Gliese 445, is an M-type red dwarf, currently located about 17.6 light-years from Earth. But the stars are not stationary. They move through the galaxy, each on its own path, each at its own speed. And Gliese 445 is moving toward our solar system. By the time Voyager 1 arrives in its vicinity, it will be only about 3.45 light-years from our Sun. At that point, Voyager 1 will pass within approximately 1.6 light-years of Gliese 445. To be clear about what this means, Voyager will not enter that star's solar system. It will not come anywhere near any potential planets. 1.6 light-years is still an enormous distance, roughly 15 trillion kilometers. The flyby will be entirely gravitational in its effects, a subtle shift in trajectory, and nothing more. But it will be the closest that any piece of human engineering has ever come to another star. And Gliese 445 will never know what happened. For Voyager 2, the stellar encounter timeline is somewhat different. In approximately 40,000 years, Voyager 2 will pass within about 1.7 light-years of a small red dwarf star called Ross 248. Like Gliese 445, Ross 248 is currently approaching our solar system. It is one of the stars that, for a period around 30,000 to 40,000 years from now, will briefly be closer to the Sun than Alpha Centauri before drifting away again. After Ross 248, Voyager 2's journey carries it toward other stars on longer timescales. In approximately 298,000 years, it will pass within about 4 light-years of Sirius, the brightest star in Earth's night sky, a brilliant blue-white star about twice the mass of the Sun, a near miss in cosmic terms, but still a tremendous distance by human standards. Looking further still, across hundreds of thousands of years, astronomers, using the Gaia Stellar Catalog, have been able to identify approximately 60 stars that the Voyager and Pioneer spacecraft will approach within the next million years. Of these, roughly 10 will come within 2 parsecs, about 6.5 light-years. The closest predicted encounter for any of the 4 escaping spacecraft in the next million years is a flyby by Pioneer 10 of a star called HIP 117795 at a distance of about 0.23 parsecs, roughly 0.75 light-years, in approximately 90,000 years. For Voyager 1 specifically, one study found that in approximately 303,000 years, it will encounter a star called TYC 3135-52-1, passing at a distance of about 0.965 light-years. Another encounter, still not close, still not captured, still passing through, like a ghost through a crowd. Here we must pause and be honest about something. Will Voyager ever be found? This is the question that underlies all of this. The question the Golden Record was created to answer, or at least to prepare for. And the truthful answer is, we do not know. And the slightly longer truthful answer is, the probability is extraordinarily small, but it is not zero. The galaxy is vast. The distances between stars are almost beyond meaningful human comprehension. Voyager is tiny, less than a meter across in its main body, invisible against the darkness at any distance greater than a few kilometers. There is no beacon on it that any civilization could detect passively from far away. And yet, some researchers point out that the statistical argument is not entirely hopeless on the longest timescales. The Milky Way contains several hundred billion stars. Voyager will, according to current calculations, continue drifting to the galaxy essentially forever, or at least for a time comparable to the current age of the universe, and perhaps far longer, over millions and billions of years. The probability of a close encounter with a stellar system and the possibility of that system harboring something capable of detection does increase. But this is speculation, not prediction. There is no scientific consensus that Voyager will ever be found. The honest position is this: it might be, and it might not be. We do not know enough about the distribution of intelligence in the galaxy, or about the long-term dynamics of Voyager's trajectory on billion-year timescales. To say anything more certain than that, what we can say is this: we tried. We attached message to it. We did what we could. There is one more thing worth saying about Voyager's long journey through the galaxy. The spacecraft itself will change, not its trajectory. That will remain on human timescales, essentially constant. But its physical integrity will slowly be altered by the environment through which it passes. The interstellar medium, though thin, contains dust particles, moving at 17 kilometers per second. Even microscopic grains of dust represent a non-trivial impact. Over millions of years, the spacecraft surfaces will be gradually eroded, pitted and abraded by micrometeorite impacts, altered by radiation. The golden record, stored in its protective gold-plated aluminum jacket, is designed to survive this for an extraordinarily long time. Researchers who have studied the question estimate the record itself could survive for billions of years, though the protective jacket would degrade over very long timescales in the harsher interstellar regions. One study that modeled the damage the golden records would likely incur over their long journey, accounting for dust clouds, radiation fields, and the specific trajectories of the two spacecraft, found that Voyager 1, due to its trajectory above and below the plane of the galaxy where dust is thicker, would likely experience more surface damage than Voyager 2 over very long timescales. But even damaged, even eroded, the record will be there, drifting, waiting. Let us talk about what Voyager is carrying. Mounted on the body of each spacecraft, Voyager 1 and Voyager 2 both, is a 12-inch gold-plated copper disc. It looks, at first glance, like a vinyl record, which is essentially what it is. It is called the Golden Record. The Golden Record was the idea of the astronomer Carl Sagan and a small team of scientists, musicians, artists, and thinkers who were given a remarkable and nearly impossible task: to create a message from humanity to the universe. Not a scientific data package, not a technical readout. A message, something that would say, here is what we are. The record contains greetings spoken in 55 languages, ancient and modern, from Bengali to Akkadian, a language that has not been spoken aloud by a living person for thousands of years. It contains sounds of earth, rain, wind, surf, thunder, the calls of birds and whales, a human heartbeat, the cry of a newborn, laughter. It contains music, 90 minutes of it, selected from across human cultures and centuries. Bach, Beethoven, Chuck Berry, a Javanese court gamelan, a Senegalese percussion piece, a Navajo night chant, a Pygmy girl's initiation song. It contains 115 images, encoded in analog format, diagrams explaining the structure of DNA, mathematical constants, the position of Earth in the solar system, images of human beings, of animals, of landscapes, of cities, of food, of birth, of death, a mother nursing a child, an athlete in motion, a sunset over the ocean. It also contains on its cover a set of instructions, written in a kind of symbolic language based on mathematical and physical constants, explaining what the record is, how to play it, and where it came from. These instructions were designed to be interpretable by any sufficiently advanced intelligence that might encounter them, regardless of what language they speak or what biology they possess. Because mathematics, the designer's reason, is universal. The hydrogen atom looks the same everywhere in the universe. The pulsar map, similar to the one on the Pioneer plaques before it, locates Earth by its position relative to 14 known pulsars, each identified by its unique spin frequency, a kind of cosmic address. Carl Sagan, when asked about the probability of the record ever being found and played, was characteristically honest. He said, "The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space." But the launching of this bottle into the cosmic ocean, he said, says something very hopeful about life on this planet. That framing, the bottle in the cosmic ocean, is the one that has stayed with people for nearly 50 years. It is worth asking, why does it matter? The probability that any civilization will ever intercept Voyager is, by any sober scientific estimate, extremely small. The galaxy is not crowded with spacecraft waiting to pick up our message. Interstellar space is enormous and Voyager is tiny. The odds are on their face, humbling, and yet the golden record was made with extraordinary care. Sagan and his team spent months debating what to include, what to leave out, how to represent a species as contradictory and complicated as ours. They argued about music. They argued about images. They worried about whether the record was too Western, too human, too narrow. They tried, genuinely tried, to represent something real about what life on Earth had been. Why put that much effort into something so unlikely? Perhaps because the act of making the record was itself the point. When you are forced to ask the question, what do we want to say about ourselves to someone who knows nothing about us? You are forced to look at yourself clearly. What is worth preserving? What do we value? What, out of everything we have made and done and felt and created, do we choose to put in a bottle and send into the dark? The answers say more about us than they will ever say to any alien civilization. The golden record is not, in the end, a message to the universe. It is a mirror. It is humanity holding up a picture of itself and asking, is this who we are? Is this who we want to be? And so we come to the end of this particular journey, or rather, to the place where our telling of it must stop. Because Voyager's journey has no end, not one we can see, not one any human being alive today, or for many generations to come, will ever witness. Let's take stock of where things stand. Right now, in 2026, Voyager 1 is more than 25 billion kilometers from Earth. A signal from it takes nearly 23 hours to arrive, traveling at the speed of light. Its engineers are fighting to keep two instruments alive. In November this year, it will cross the threshold of one light day from home, the first human-made object ever to do so. Its twin, Voyager 2, trails behind it, also in interstellar space, also fading. In the coming decade or two, both spacecraft will go silent. In 40,000 years, they will make their closest approaches to other stars, pass it within a light year or two, and continuing onward. In hundreds of thousands of years, they will drift through the arms of the Milky Way, encountering star after star, influenced by each one's gravity in ways too subtle and slow to call anything but geological. In millions and billions of years, we cannot say. The calculations become uncertain. The galaxy itself is changing on those timescales. Stars are born and die. The positions of everything shift. But Voyager will keep going. There's a thought that I want to leave you with. We are a species that has existed in our current form for perhaps 300,000 years. We have had writing for about 5,000. We have had science, in the modern sense, for maybe 400. We have had spaceflight for less than 70. And in that tiny, almost laughably brief window of cosmic time, we managed to build something that is now in interstellar space. Something that will outlast our cities, our languages, our civilization itself. Our sun, something that carries inside it the sound of mother laughing, the opening notes of Beethoven's Fifth Symphony, the heartbeat of a living human being, That spacecraft will be drifting through the galaxy long after everything we have ever built has crumbled to dust. Long after the last person who remembers the Voyager program is gone. Long after the Earth itself is consumed by the expanding sun Voyager will still be out there, silent, alone, moving through a universe that will, in all likelihood, never know it exists. And maybe that is enough. Maybe the point was never be found. Maybe the point was to go, to look up, to reach, to build something that said, we were curious, we were brave enough to try, we cared enough to say hello, even knowing no answer would come in our lifetime, or in the lifetime of our civilization. Carl Sagan once wrote that we are a way for the cosmos to know itself, that these atoms, assembled over billions of years of stellar evolution into the improbable shape of a human being, have developed the capacity to look outward and wonder, and not just wonder, but act on that wonder. Voyager is that action made physical. It is a spacecraft. It is a scientific instrument. It is a time capsule. It is a message. But above all, it is proof, drifting now through the cold dark between the stars, that something on a small pale blue in an unremarkable corner of an ordinary galaxy once looked up and reached